How's it going, Paco?
It's going well enough. Thank you.
Yep, yep.
How about you?
Going well. It's going well. A little busy, but overall good. What classes are you taking this semester?
80/30 and uh 8400.
Oh, algebraic number theory.
Yeah,
Oh, cool. Nice. How's that class going?
going well.
Cool. Yeah. I took that class fall 2017. I think he's teaching in the same book. So he's
Yeah.
starting off with quadratic fields, right?
Mm-hmm.
Yeah. Yeah. And then he jumps into the general case. Yeah, it's pretty fun.
Oh, what am I doing? I was supposed to go out, but I figured never mind. So I had a mask.
Nice.
Yeah. Anyway,
I forget, did you end up taking any qualifying exams this semester?
no, because I was busy moving in.
Ah, gotcha. That's a fair excuse. Fair.
Yeah.
Hello.
Uh,
Hello.
Hello.
Strange that some people need to be admitted and some people don't. I haven't figured out why that is yet. Maybe one day
Yeah.
I'll learn. All right. Well, welcome back, everyone. There's not too much to say in the way of announcements. I did just now upload some more problems on the ELC webpage. So there's now a lot of problems which are these are about a lot of them are exploring the notion of cohomological dimension of a group, which is something that came up at the end of the problem session. Yeah, I mean, among other things, it's the minimal length of a finite resolution of Z as a ZG projective, finite projective resolution of Z as a ZG module. If there is a finite resolution, and it's infinity if there isn't. Equivalently, it is the largest non-vanishing index of group cohomology for that group. And so there are some exercises which relate the cohomological dimension of G to topology, actually. So in particular to the in particular to the topological space unique up to homotopy equivalence, the Eilenberg-MacLane space KG1. And so in fact, there are some groups for which you can compute the cohomological dimension by knowing what the corresponding Eilenberg-MacLane space is. And so those are, if you like topology at all, those are some fun exercises. And I guess it really goes in a different direction because one of the exercises, if you put, yeah, it's literally one of the exercises. It's not so deep that the only chance that your group has of having finite cohomological dimension, if it's non-trivial, is it needs to have every non-identity element has to have infinite order. Okay. So in particular, every non-trivial finite group is going to have infinite cohomological dimension. And so what that means is that there is a closely related but different notion of cohomological dimension for profinite groups, which we'll study later. So this is really, you know, if we wanted to emphasize at the moment we're doing cohomology of discrete groups. Okay. All right. Any questions? No. All right. Well, let's get back into it. Yeah. So maybe we'll see. I trying to think of like how much time I should lecture each, you know, for each lecture, it's for it to come out to about the right time. So we'll see. Maybe I'll lecture until like 3 or so today while recording it. So anyway, we'll see what happens. Okay, so we were in the middle of a somewhat technical discussion of the standard resolution of which is a particular free resolution of Z as a ZG module, which gives us a concrete description. It gives us, in fact, it gives us more than one concrete description of group cohomology is literally co-boundaries, cocycles modulo co-boundaries. And so, okay, let's begin by recalling what we did so far. So for a non-negative integer n, E sub n is just Cartesian product of n plus 1 copies of G. We view this as a left G set with the obvious diagonal action. It is certainly a free left G set. No non-identity element of G fixes anything, and it's diagonal action on copies of G. So by an exercise that I stated last time, if you take the free Z module on a free G set, then you get a free ZG module. Okay. So yeah, so Pn is a free ZG module. Again, its rank is going to be the cardinality of the Cartesian product of one fewer copies of n copies of G. And then, well, we skipped the content here, and I am going to skip it because it's proved perfectly well in Harari's book. But so you in a relatively innocent way, you can get a resolution here. So the D0 is a map from P0 to Z. Well, P0 really is essentially it's a free ZG module of rank 1. And if you just look a little bit at what the definition is, like it really is ZG. And so this D0 really is just the augmentation map that sends every actual group element in the group ring to 1. And then for all n greater than or equal to 1, we need to define some kind of boundary map. Again, I have in particular, again, I have a free Z module. So if I'm trying to define even a Z homomorphism, I can tell you where the basis goes and everything else goes where it needs to by Z linearity. So I'm defining this, strictly speaking, I'm only defining the boundary map here on, on elements of En. But okay, that's a Z basis for the module. So you just extend by Z linearity, and it's fairly straightforward. So we have this n plus 1 tuple, and we kind of we're trying to get a Z-linear combination of n tuples. And so hopefully you've seen this sort of thing before somewhere. So we remove each one of the elements, we add them up with a sign discrepancy. Okay. And then the lemma here again is that again, these are the PNs are definitely free ZG modules, and so we just have to check that that this is exact. Okay, so again, as I recall, checking that it's a complex, in other words, that the composition of any two of these maps is equal to 0 is you just write out like 3 or 4 lines, and it's straightforward, and then checking that everything that is in the kernel of one map is actually coming from the images. You have to do something. Okay. And so that is in Harari's book. Okay, so we move on. And so now we have a resolution, so we can use it to compute. We can also use it to compute homology groups, although I don't think we have time to talk about that explicitly here. Maybe we'll come back to it later. Anyway, we can use it to compute cohomology because, as we saw, since the invariants can be interpreted as the invariant functor is Hom of Z blank, then therefore its derived functors are the X functors of Z blank. Okay. And so what do we do for derived functors? We have our projective resolution. We strip away the Z. We apply the functor, which is the Hom functor here. Okay, and then we take the cohomology. Okay, right. And so what is each one of these? So now in order to do this, we should to make this concrete, we should interpret the ZG Hom of Pn into M. Well, as we talked about last time, a nice thing here is that the ZG Hom is actually the G invariance of the Z Hom. Now, Pn is a free Z module, so we're just sort of concatenating universal properties. And so here, well, again, if I have a map from this is I mean, I'm sort of taking care of the G invariance at the end, but on the inside, I have a Z-HOM from a free Z module with a certain basis into M. Oh, I love that. That's canonically identified just with the collection of all set maps from the basis into N, and En is again just our notation for G to the N plus 1. And so, okay, so the nth term here in the complex is the G invariance of just literally the set of all maps from Gn plus 1 into M. And so how is G acting on these, on these maps? Yeah, it's acting, it's acting according to the adjoint G action that I defined before, where you act by G inverse on the, if you have a map between G sets, then usually, maybe later in this lecture, we'll see something that looks like it's an exception, although it's kind of related secretly. The most reasonable G structure to put on a HOM between G sets is you act on the inside by G inverse and you act on the outside by G. And then we saw that the G invariants are the ones that are actually G maps. And so, okay, so this is the collection of all guys from Gn plus 1 to G, so that if you act on the inside by G, that's the same as acting on the outside by G. Okay, and acting on the inside by G, again, it's just the diagonal action. You act on each coordinate. Okay, so this is quite concrete. So script Kn is exactly this. It's the collection of all just set maps from G to the N plus 1 into M that satisfy this simple G equivariance property. Okay. And then it's not so hard to see at all that, well, what are the, we have pullback maps here, right? So before, so here we have, so we have a complex here, right? But then I defined boundary maps from Pn to Pn minus 1, right? So if you think about it, okay, I can do it at 0 and 1, just as well. I think of this as being, I don't know, like an n minus 1 and an n. And so if I have a HOM from Pn into M, then I can, wait, I think how do I want to say this? If I have a map, if I have a HOM from Pn minus 1 into M, there we go, then I can compose with the map from Pn to Pn minus 1, and then I'll get a HOM from Pn into M. Okay, so that's what the, abstractly, it's not a problem to see what these coboundary maps are, and then you just have to kind of square this. You just have to square this explicit description down here with this explicit description up here. I'll let you think about that. And then you get the following completely explicit description of the coboundary map, which is basically the same as what we had before. So what is the coboundary map applied here? So you take the coboundary map. So you have a function from Gn plus 1 into M. Its coboundary map should be a z-linear combination of functions from Gn plus 2 into M. And so, okay, so you feed me, sorry, not a z-linear combination. It's the coboundary should again be a function from Gn plus 2 into M. Sorry about that. Okay, and so you feed in, going from 0 up to n plus 1 is indeed n plus 2, and it's basically the same recipe that we had before applied to F. Okay, so this is a completely explicit description of the cochain complex, and so this does compute the group cohomology. Okay, so again, maybe we might want to do something else. We do, but you can't. You can't really say that this is not this is a perfectly concrete description of the group cohomology. And so these guys can, this interpretation this would be called like the homogeneous version of the standard cochain complex. And there's a lot of words. People sometimes use like bar resolution. I think that's another synonym for this type of thing. But anyway, so probably the most useful description is that these are called homogeneous cochains. Okay. This is, however, not the only thing that we want to do. Sometimes every once in a while, you actually do kind of want to use homogeneous cochains, but there's a way to simplify it slightly. So what's sort of the idea? The idea is that, well, one thing that could be a little bit easier, I mean, it's concrete, but it could be even easier, is that here, you know, the terms in the cochain complex are not all maps from Gn plus 1 into M. They're only the G invariant ones, right? And again, the G action on Gn plus 1 is so simple. It's a free G action. And so the idea is maybe we can kind of use up the G equivariance here. We kind of have one more degree of freedom than we need. This is sort of the idea. And so if we use up that last degree of freedom, we should be able to get a slightly simpler description. And if I just were to write that down right away, you'd be like, whoa, why did you do that? So let me do the more natural thing first. So so the idea here is that because we are assuming G equivariance, what is the G equivariance on G to the n plus 1 by U? Well, again, you know, there's a unique element. What did I say? The G orbits on G to the n plus 1 correspond to elements of G to the n, because you can let G act on the first guy. You know, if you started with G0, G1 dot 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 Gn, and then you act by G0 inverse, then you're in the same G orbit, and now you've made the 0th coordinate equal to 1. And so again, because it's G equivariant, a G equivariant such function is going to be uniquely and freely determined by its values on tuples where the 0th coordinate is equal to 1. So that's what I hope I just explained. You can certainly evaluate on this, you know, on this subset, and if you know what the function is doing on this subset, and you know that it's G equivariant, then you can, I guess that's what I'm explaining right here. So then you can do it on an arbitrary one, right? So f of G0 dot 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 dot. Oh dear. Can I really not have a pen on me? That's ridiculous. No, I cannot. Okay, so right. Okay, so again, you pull out the G0, and so now I'm using up the G equivariance, and you see that indeed I didn't lie to you. So if you know what your element of Kn is doing on guys whose 0th coordinate is equal to 1, then that's what it's doing on all guys. Okay. And so therefore this suggests, why don't we just use up one of the coordinates? So let's let regular Kn be the collection of all G is a bad choice. All functions from Gn into M, okay? And then there's just kind of an obvious isomorphism of G modules here. So again, you just I'm just making up some notation. So I take a guy, this bigger one, and I send it to F bar, where F bar now of an n tuple, G1 through Gn, is the original F where you evaluated it at 1, followed by G1 through Gn. Okay. And so it's no problem to see that this gives us a Z module isomorphism from the first guy to the second. Okay. And so therefore, you know, by nothing, just by transport of structure, I can define the complex in terms of Kn instead of Kn plus 1, right? And so the idea is, you know, I like, but essentially I've just simplified my Z. I've given a slightly simpler description of my Z module Kn. That's all I've done, right? So rather than say it's the G equivariant functions on Gn plus 1, I've just explained to you why you can also view it as the set of all functions on Gn. Okay. via this maneuver. And so yeah, so then, well, what should the co-boundary map be? Well, this is what transportive structure means. It means, you know, you've adjusted each side via an isomorphism. So dn is exactly what you get by going up via the reverse of the isomorphism, applying the old co-boundary, and then going down via the isomorphism. So okay. Right, and so of course that works to compute the cohomology as well. Basically all I've done is like change a basis. Okay, so there's nothing going on here other than kind of an alternative description of the underlying Z module here. It turns out though that we should change basis in a trickier way to get a good formula. So let me motivate that by actually computing the coboundary for n equals 1 here. So I'm supposed to compute the coboundary here. Yeah, so I'm writing it as sort of f prime as being the image under f of my isomorphism. It is an isomorphism, so every f prime is the image under some f. Okay, so I'm trying to compute my coboundary down here. So what does this recipe say? It says compute the coboundary of f attached to 1 g1 g2. This is exactly what the formula up at the top for the coboundary was. Okay, and then the idea is, well, now I need to kind of re-express this in terms of f bar, which only takes one argument rather than two, and we know how to do that, right? So so again, f of g1, g2, because f is the g equivariant one, I can pull out the g1. I don't have to pull out anything because these have 0th coordinate equal to 1 anyway. And then I go back the other way. So f of 1, blah, 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 is f bar, strip away the 1. Okay. And so that's what it is. Okay, so the coboundary in this new basis of g1, g2 is equal to this guy. And you look at this and you're like, oh, if I'm cheating and I know what the coboundary is supposed to look like, you know, in first cohomology, that's not what I wanted. Okay, so it's a thing, you know, it's correct in the sense that it computes the cohomology, but this should be simplified more. So if you stare at this, what do you say? You say, I'm not liking the look of the G1 inverse over here, right? And so what change of variable does this suggest? This suggests, oh, hold on. Let's see. So, right. Yeah, so this suggests changing variables from G2 to G1, G2. Okay, so if I write that here, I wrote it down for G1, G2, I got an ugly formula. If I write it down and I apply it to G1, comma G1, G2, okay, so wherever you see G2, replace it with G1, G2. Yeah, I like that better. Okay. And so, I mean, again, this is really just a, you know, whatever, you know, every single element of the, as G1 and G2 run through all elements of G, all pairs of elements of G, so does G1, comma G1, G2. So I'm not losing, it's another change of variable, right? So I'm not losing any generality. So I go back and say, I didn't actually make the, you know, in changing from homogeneous to inhomogeneous, I should have done something weirder. And now I say, aha, finally, I figured out what I want the weird change of variables to be. The weird change of variables has not been foisted upon me by these confusing textbooks, right? So we want f bar of G1 through Gn to be 1, G1. We only did it for n equals 1, I guess. So, you know, there's a little bit of a, anyway, so this is what we should be doing. So we should be sort of correcting in this way where we kind of multiply by more and more elements in order to do this. Okay. Right, and now let me redo the n equals 1 case again so that you can see that we did the right thing. Okay, so now if I redo the n equals 1 case, so now I get df bar G1, G2, okay? And so now I use, before I was just doing one G1, G2, but I decided that I like it better if I have an extra G1 here, so that's I can do whatever I want. I'm just changing variables, right? And so then we go back through and then, right, so now again, it's just the same formula for the co-boundary in terms of the homogeneous cochains where we, we omit here, first we omit the 0th element, then we omit the first element, then we omit the second element and alternate them. And then we do, I'm basically doing the same calculation that I already did before. I just want us to really believe that we've done the right thing. Okay, and so we do it this way, and we get this, and we say, yeah, that's what I wanted to see. Okay, so in particular, this is just the map. So the cochains are the ones where, by definition, the functions f bar, I can stop calling them bar, they're just functions. The functions for which when you hit them with d, you get 0. And so therefore the ones where this thing is equal to 0 are the functions where f, okay, let me not call it f bar anymore. The ones where something phi of g1, g2, if I bring this to the other side, phi of g1, g2 is going to be phi of g1 plus g1 times phi of g2. And again, if you're cheating and you've seen the one co-cycle condition before, that's exactly what it should be. Okay, and so the lemma here is that in general, this leads to, I just did the n equals 1 case. I don't, if I'm not mistaken, the case of general n is not really any harder than n equals 1. I just wanted to do a faster calculation. And so in general, still using the, it's reasonable to do the, do the f bar here. Okay, so so the co-boundary is equal to, wait, hold on. I think let me think for a second. Here I do want bars. Okay. As I got in the n equals 1 case. Okay. So right. So the point is that once I've said it this way, it doesn't need to be f bar anymore. I just call it whatever function from g to the n into my module I want. Okay. Yeah. So you pull it all together, and finally we're getting the most standard formula here. So this is our co-boundary map this is our co-boundary map. Okay. So we have a function from g to the n into m, and then the co-boundary map takes it to a function from g to the n plus 1 into m. What function is it? It's this function. Okay, so that's what we were hoping for. And so therefore, and again,
why is this simpler than the previous thing?
It has one fewer variables.
Okay.
That's why. Yeah. Okay. So that's the only reason. Okay. Okay. So yeah, and so now we get. It's I didn't say forget about the homogeneous cochains forever. That they come up sometimes. But yeah. Okay. So all right, and so then now just by definition, whenever you have a cochain complex, you define the co-boundaries, the nth co-boundaries to be the kernel, and you define the n co-cycles, the n co-cycles to be the kernel, and you define the n co-boundaries to be the image. And then just by definition, again, I really did just find one cochain complex that by the magic of homological algebra computed my group cohomology, and then I just changed variables twice, I guess, on that, well, not really twice, once and then a better time. And so of course, this still computes the group cohomology. And so now we have the most standard so the description of the group cohomology using cochains modular co-boundaries. Okay. Right, and of course I could have just made this definition to begin with, but again, the point of doing it this way is that I know that these guys piece together to give a homological delta functor. So all the, the machinery of homological algebra is on my side now because I derived this simple expression as coming from a projective resolution. Okay, and so let me just write out some things for the sake of concreteness. So most of all, we care about the case n equals 1, followed by the case n equals 2. To be really honest with you, I have never in my life done explicit computations with group homology 3 or more, not once. Okay, so 1 and 2 are kind of where it's at, and 0. Okay, so the 1 cocycles, this is exactly what we derived before. So these are kind of called twisted homomorphisms. So it almost looks like f of g1 g2 is equal to f of g1 plus f of g2. And that way it would be if the g action on M were trivial. In general, we sort of twist. Yeah, so this is kind of twisted homomorphism. Okay, so we start with a homomorphism, but then we twist back by acting by the G1. And then again, what are the co-boundaries? Is it just the ones that come from the 0 guys? And so I leave, this is certainly very straightforward. I leave you to check that the 1 co-boundaries are the functions for which there is an element m and m, such that for all g and g, the function is given by g. Oops. I guess it should be an A. There's an A and M such that for all G and G, f of G is equal to GA minus A. And if you've never seen this before, you should certainly check that that the co-boundaries are living inside the cocycles, and so in particular that the cocycle condition is satisfied for this. That's almost immediate. Okay, and so that's great. Like already the 1 cocycles and the 1 co-boundaries are probably the most important thing. And as I said, in particular, we get something very simple. If the G module happens to have trivial G action, okay, then what happens? Well, as I said, I don't care whether I act by G if my action is trivial, right? And then it is literally just okay, so it's like a multiplicative. I'm writing the group law on G multiplicatively, and I'm writing the group law on M additively. Fine, that's exactly what I'm doing. It's still a hom. Okay, so it's literally just the homomorphisms from G into the additive group of M. And then what are the co-boundaries in this case? Well, if the G action is trivial, then GA is equal to A for all A and M, and so the co-boundaries are equal to 0. And I guess I'll write it. And so therefore, the first, in the case of a trivial G module, then the first group cohomology is nothing else than the hom from G into M, which of course factors through the abelianization because M is a commutative group. Okay, so that's useful. Okay, so that's the case n equals 1. And then again, I'll write down the case n equals 2, which is the only other case that you sort of see so explicitly. So what are the 2 cocycles? I mean, I'm just writing down the conditions so that you can look at it. So these are the functions from G2 to M, such that for all G1, G2, G3 in G, we get this condition. So if you like, bring the well, whatever, I'll just write it like this. So G1 times f of G2, G3 minus f of the G1 times G2, comma G3 plus f of G1, comma G2, G3 is equal to f of G1, G2. Okay. That's a really strange, what does that say there? Pretty sure that should be f of G1, G2. Okay. Okay, and so let me just make a quick comment in terms of the origins of the subject. I think that actually this is where it all started. And so this type of cocycle condition already looks kind of weird. If it's got to come up somewhere, but it does come up somewhere. So just briefly, H2GM This is for a different course, I'm afraid. So I think that Harari makes the remark as well, and so am I. I'm not going to stop to prove. I can certainly give you a. I'm sure that by the way, Rotman has a very nice GTM on homological algebra. It's really, really long, and it's so long because he just carefully explains everything very patiently. And it's pretty focused towards just like basic group and ring stuff. So I can virtually guarantee that Rotman will have a very nice explanation of this, of what I'm about to say. So yeah, okay, so you have a group extension. So what's a group extension? We're not working with commutative groups here, by the way. So M needs to be commutative, G does not. And so I have a normal subgroup of a group whose quotient is G. And now when I have such a group extension, an extension of a group G by a commutative group M, that's the lingo. So then that actually just this extension puts a G module structure on the kernel M. So why is that? I remind you, what do? You take a G in G and you lift it to an element of E. That's a search action. So you lift it, let's call it G tilde. And then I let G act on M. This is what I'm trying to tell you, like how does G act on M? It acts on M by conjugation by G tilde. And then if you've never seen this before, you have to ask, well, how do you know that's well defined? You chose a lift. Great, just check. So, you know, if a different lift would have been of the form G tilde times U for an element of M, because after all, M is the kernel. So that's the ambiguity in the choice of lift. So what if you conjugated by G tilde U instead? Then you would get this. And then, oh, thank goodness, I really did use that M was commutative. And so M and U are both inside this commutative group, so the conjugation goes away. Okay. So if you have a group extension, then it puts a G module structure on the kernel. Okay. Right, and so it turns, yeah, so the fact here is that there's a certain equivalence relation on group extensions it involves a you know, like a morphism from one of these group extensions to the other. It's probably what you would guess, somewhat, you know, sort of functorial. And then the second group cohomology is classifying equivalence classes of these group extensions. In particular, the trivial class here, right? The cohomology. I mean, this is certainly a Z module, by the way, and so it has a zero element. And so the zero element represents the split extension, okay? Okay, so here we go. And so, yeah, I'm not doing all this, but I'm really not doing it, but in like very little space, if I wanted to, just using this data, using this extension, I could define a 2 cocycle. Okay, maybe this extension, and then maybe I make a choice in order to define the cocycle in terms of lifting stuff. And so it turns out that among other things, again, the cocycle is cohomologous to 0. So the cocycle is a coboundary if and only if the extension splits. So what does it mean for, you probably know what it means for like something in a, you know, in a abelian category or something to split, but these are non-commutative groups. So what does that mean? I mean, it means a similar thing. It means that that there is a, you know, there is a section here in the category of groups, and that's the same as saying that, you know, so it's the same as saying that you have this kind of complementary factor. The only thing is that the M is necessarily a normal subgroup. This complementary guy G is not necessarily normal. So you don't necessarily get a direct product. In general, you only get a semi-direct product. So that's what splitting of the extension means in this case. And it is my distinct understanding that this is really the origin of group cohomology. People were doing group theory, and they wanted to understand. So there's certain classes of pairs. So this is actually one of the most important things to try to do in all of pure group theory. So, you know, you try to build groups out of simpler groups, right? And so if I give you just two finite groups, I mean, they could even be like cyclic groups of prime order or something. and I say, in how many ways, like how many groups of order, p squared, do I have that are built out of, a cyclic group of order p? And the answer is that up to isomorphism, there are 2 of them. You could take Z mod p direct sum Z mod p, that would be the split one. Or there's another one, which is the cyclic group of order p squared, which is not semi-direct product. Okay, and so this is one of the most important problems in all of group theory. So, if you have, suppose I have a finite group, right? And then what do? You have the Jordan-Holder factors. You write down some maximal series where each guy is normal in the next guy, right? And the Jordan-Holder theorem tells you that the successive quotients, which are finite simple groups, are that sort of multi-set of composition factors is well defined up to isomorphism. And so then it's like sort of like a Humpty Dumpty sort of thing. Like if you come with your finite simple groups, then you try to put them back together into your group. And in general, there's lots and lots and lots of different ways to do that. And that's kind of what makes finite groups really complicated. But there are certain conditions under which if I take these 2 simple pieces, or whatever, if I take 2 pieces under certain group theoretic conditions, there's no non-trivial way to put them together. There are certain pairs of groups, G and M, such that every extension of G by M is split. And there's a certain theorem along these lines. I guess I don't need to state it. You can look it up if you want. I was lucky enough. My first graduate algebra class did include the Shor-Zassenhaus theorem. This was at the University of Chicago, where group theory is popular. So there is a theorem in finite group theory called the Shor-Zassenhaus theorem, which gives a criterion in terms of I think coprimality of the orders or something like that, where every extension of one group finite group by another is necessarily split. And how do you prove the Shor-Zassenhaus theorem? You prove it by developing the rudiments of group cohomology. Okay, so that's where it's coming from. The first homology group has an interpretation in terms of extensions, group extensions as well. All right. Yeah, so now some corollaries here. This is a very simple but important corollary. If the group and the module are both finite, then it follows that all the group cohomology groups are finite. Why is that? It's obvious, because the group cohomology is the quotient of the cocycles modulo the coboundaries. Again, these are both just Z modules. But even before you take the quotient, the collection of cocycles, listen, they're maps from G to the N. If G is finite, then so is G to the N into M. And look, the collection of all maps between 2 finite sets, they're only finitely many. So already at the level of cocycles, each of these cocycle groups is finite if both G and M are finite. So surely the quotient of this finite group is finite as well. Okay, so that's very useful. I think as Harari remarks, you don't, if for some reason, if you're like, why do I have to, do I really have to mess with, dirty my hands with these cocycles and coboundaries? Shouldn't there be some pure thought way to prove, this result? Yeah, there is, but why are you arguing with us? This is a good way to do it. Okay, and then again, at the end, this is, I'm kind of found myself giving the second half of one lecture and the first half of another lecture for a little while here. So this brings us to the end of lecture 3. So as I mentioned before, if you take the resolution, this P bullet standard free resolution that we defined at the beginning, and then you just do the group homology thing rather than the group cohomology thing. So instead of taking hom from Z into nope. Instead of taking hom from that resolution into M, you tensor that resolution with M, and then take homology. Then that's how you compute group homology. And so again, in just the same way that we sort of carefully, unwound that and got a very concrete description of group cohomology, in terms of cochains and coboundaries, you could also get a very concrete description of group homology in terms of chains and boundaries. Okay, so that's a thing. Again, it might come up. I actually looked ahead. I was like, why in the world is Harari not discussing group homology? Like, I know that like chapter 2 is like Tate cohomology. I know that Tate cohomology is when you splice together group cohomology and group homology. Like, is there some amazing way that he's going to discuss Tate cohomology and never bring up group homology? Like, no, in chapter 2, he's like, oh, you can do group homology too. So we're not losing any ground by doing it this way. But anyway, so at the moment I'll leave this as an exercise. By the way, it is admittedly true that group cohomology is just somehow more appealing than group homology. Okay, we can ask ourselves for the reasons, why that's true. It's kind of always true though, right? Like, I mean, isn't topological cohomology a little better than topological homology as well? It kind of is, right? I mean, I think, like, does anyone want to say why? I think I have a reason. Like, if you asked me the question, I know what I would say. But if I asked you, why is cohomology better than homology?
The functor is nicer.
The what?
The functor, like the invariants, are nicer than the co-invariants, I guess.
Are they? Seem pretty similar. I mean, you're saying like, oh, I like sub-objects better than quotients, and I'm like, no, that sound kind of similar to me. Anybody else?
Because the cup product.
Yeah, exactly. That's what I would say. So there are product operations in cohomology, right? Both topologically and in the group theoretic language, and then in homology, there's product like things, but it doesn't work. So there's intersections and whatnot. Yeah. So that I think is the answer. So even if you do singular cohomology, then you get a ring, right, under the cup product, and that's great. And so something similar, something's happening. We're gonna have a cup product map in group cohomology as well, which will be extraordinarily important once we actually get it. I mean, it's a very natural thing. If you're doing like Galois cohomology of elliptic curves, then cup products. Yeah, so I think that I think is the answer. I think the answer is that doing cochains rather than chains allows us to define products. We'll see when we get there. Kind of. Okay. Any other questions about this? I'm about to move on to a new topic. I don't know if you can tell, like I've always found this discussion of like standard resolutions to be like slightly confusing. I think I admitted this already. Just I don't know. Not so much that like I don't understand it, but I feel like people should do a better job when they introduce it. Okay. One could have done even a better job than this, but it was still better than what I saw. Any other questions? All right, let's move on. So the next thing I want to talk about is induction and co-induction, and then this is going to lead into something called Shapiro's lemma. So this is very important. It definitely has it's technical enough so that maybe we should begin by kind of selling it a little bit, and not much more technical than that. So suppose we just have a group where, hey, we're working in the category of G modules, right? And it's a tricky category, right? As we've seen, like it's definitely not a semi-simple category and blah, 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 blah. Like it's there's some difficulty here. And so what kind of tools would we expect to use to study this rich, algebraically, not completely transparent category? And I think the first idea is, maybe we should really exploit the idea that we don't just have one group at a time. You can study a group, of course, by studying its homomorphisms to other groups, right? I mean, again, it's the Grothendieck philosophy. It would be like the most pretentious way to put it, but there is a functoriality in G here. So if you have a group homomorphism from G to G prime, then that certainly induces a ring homomorphism on the group rings. again, for instance, you can certainly appeal to the universal property of the group rings, or you can just argue completely directly, like what on earth is this homomorphism? Of course, every element of G sitting inside the group ring should go to its homomorphic image in G prime, and then you should extend Z linearly, and that's great if that gives you a homomorphism of rings, and sure it does. Okay, so the induced homomorphism is exactly what you think, and so therefore that gives us a functoriality, right? So this is more of a functoriality now in terms of in terms of module theory, right? Also, if you have a module over a ring, then you can use homomorphisms to and from other rings to understand categories of modules. And in commutative algebra, I'm not saying like we could have done more with it if we really wanted to study module categories or something, but that certainly is a familiar idea. And so in particular, using this, any kind of G module can be pulled back or restricted or whatever you want to call it, right? If you have a ring homomorphism R to S and you have an S module, then you just precompose and that makes it an R module. That's the most familiar operation on sort of change of rings. Right, and so of course, every group homomorphism can be factored as a quotient map followed by an inclusion. That's like what the first, the fundamental isomorphism theorem for groups. That's basically what it's telling us. And so, okay, quotients are nice too. We'll get there. But at the moment, I want to talk about subgroups. Okay, so an inclusion of groups is essentially a subgroup. And so in particular, every G module can be restricted to an H module for every single subgroup of the group G. Yeah, that sounds useful, right? It kind of sounds useful, and it kind of sounds like whether we like it or not, we're going to have to worry about it, right? You could look at it either way. And so we have this very obvious, okay, I'll say it, functor, forgetful functor, from the category of G modules to the category of H modules. And so, like, shouldn't there be something in the other direction? Like, you go around the block a few times mathematically. You're expecting something in the direction, but now the situation is a little bit unexpectedly rich. There's two things in the other direction, actually. So that's what I want to talk about. So right. So conversely, given an H module, it'd be nice to push it forward, whatever that means. It just means arrow in the other direction to a G module. But again, there's two ways of doing this, okay, in general. And again, Harari kind of ruins this a little bit. I don't like his. He says absolutely nothing wrong. He just expositorily he doesn't say it the way I would prefer. So here's the first way. The first way I previewed, this is like one of the very first things I said in the course, right? I like blathered on about bimodules for a little while in order to define exactly this. So this is called, yeah, maybe I should be more clear. So either way, so there's two things to do, but first of all, M is an H module. And so I would like to sort of cook up or induce a G module. And so here's one thing I can do. As I said, I can just tensor from ZH to ZG. Yeah, and I set this up. So this is a bimodule thing. So ZG, like every ring R is an RR bimodule. So ZG is a ZG-ZG bimodule. So if I forget a little bit, it's in particular a ZG-ZH bimodule. And M is a left ZH module. So it's a ZH-Z bimodule. And you do the tensor product and the inner rings kind of evaporate. And so therefore you get that the tensor product is a ZG-Z bimodule, which is indeed a left ZG module. Okay. And again, if this scares you, or maybe even if it doesn't, you should just think of what this is actually fairly concrete. If you were going to write this down, it would come out in terms of formal Z-linear combinations of elements of M indexed by the cosets of H and G. Okay, so it's not, you could define this thing with its ZG module structure without saying tensor product if you didn't want to. That's not the best way to do it. It's nice that it's a tensor product, but you could. Okay. So, but that's what's in one corner. But now the plot thickens because in the other corner we have something else, which is called co-induction. Okay. Oh dear, I seem to have misplaced my M's and my A's. So M M. Okay. So instead of doing the tensor, we do the Hom. That's really the only difference, right? So here I did tensor ZG blank over ZH. Here I'm doing Hom ZG blank over ZH. Okay. Right, and now again we had this, we had this. What does it mean to do a ZH module Hom? Well, it means do a Z module Hom and then take the H invariance. But now here I really need to tell you what the G action is, and here's where it's kind of not exactly what you might have wanted. The definition, I stand by it, for the G action is G dot f of x is on the inside you multiply by the right. Multiply by G on the right. So again, I think I took a couple different stages in my notes here as to like how to explain this. So let's just try the basic. Maybe maybe you were let's see. By the way, this thing on the inside is ZG, right? So it's a ZG bimodule, so it makes sense to either do it on the left or on the right. So it's legal. You might have been expecting a Z by G inverse on the left, and then kind of in general, by the way, like if you're acting by G inverse on the left, you could switch to acting by G on the right, just in terms of making it an action. So that's all I'm going to say at the moment. Again, I think I have some things to say soon about comparing this. It would not make sense to do like G, F, G inverse, because on the outside, after we apply F, at the moment, we only have an H module. So we can't act on it by G on the outside. Anyway, this is our definition. Okay. So the co-induction is the ZH Hom from ZG into M, and then we give it, reasonable looking G module structure. It doesn't directly follow any of the recipes for putting G module structure on things that we've given. So that's induction and that's co-induction. And at the moment, okay, well, so I'm gonna talk about it for a while. But at the moment, I guess all that's clear is that both induction and co-induction are arrows which are going in the other direction. So these are two ways of starting with a ZH module and giving us a ZG module. So there's a very important special case, which is, all right, you can do this from the trivial group. Okay, so in that case, you just start with a Z module. And if the group is trivial, we just ignore it. So it's just int from nothing up to G of just a Z module, A. Well, there you just tensor. Again, it literally is just the special case where you take H to be the trivial group, and the group ring over the trivial group is just Z. So here we just do the ZG tensor product. Okay. And then the co-induction is the same. We do the Z Hom from ZG into A. Okay. And so a module, I guess the lingo here is that a G module, which is isomorphic to such a module, is called induced. Okay, so a G module is induced if it is of the form up to isomorphism, of course, of induction from the trivial group. And this type of ZG module is called co-induced. All right, well, we're on the board, but again, where are we going with all this? So now, yeah, this paragraph I didn't love so much. Well, let me just try to make the point. In general, if you're trying to switch from left to right, if you had a left G module structure just in general, and you wanted to make a right G module structure, then what should you do? Well, you already have the left action. It doesn't make sense to define M.G to be G.M because left actions and right actions don't work exactly the same way. That just wouldn't have the homomorphic property. But if you stick a G inverse in, then that'll make it work. So that's already, makes a certain amount of sense. And then if M is equal to ZG, then I claim that this way of switching from, left to right is sort of taking the standard left structure to the standard right structure. Again, this is not of crucial importance for me to go through this so slowly and carefully. This is really just an ancillary remark. But what's really going on here, what's really going on here is that if you have a module over a ring, right, and if you want to switch the side of your module, what should you do? Again, you can't do that in general. If I have a left, here I did it for a group, right, group action. But if R was a non-commutative ring, I can't make a left R module canonically in general into a right R module. It just might not be possible. What can I do? I can canonically make a left module, R module, into a right R op module, where the opposite ring is the same underlying abelian group. Have you seen this before? So the opposite ring. So if R is a ring, probably not commutative, otherwise this is totally trivial. So then you can define the opposite ring to be, R with the same addition, and then this sort of opposite multiplication, which is exactly what it sounds like. So the opposite multiplication is the original multiplication in the opposite order. Okay. And it really, a ring really may or may not be isomorphic to its opposite ring. Obviously, if it's commutative, it is. And so, yeah, so in general, if you want to switch from left modules to right modules, the ring switches to its opposite. But again, whereas not every non-commutative ring, if I pick a non-commutative ring at random, I do not expect it to be isomorphic to its opposite ring. But the group ring is, because the map from G goes to G inverse is induced. Every group is isomorphic to its opposite group. The map G goes to G inverse is an isomorphism from the group to its opposite group. And so that induces a ring isomorphism from the ring to its opposite. Okay, so that kind of explains a little bit of what's going on. But if you're like, wait, what are you really getting at? I'll say more later. Okay, so I'm just trying to explain a little bit this. Maybe you were expecting a G inverse of M, and instead you got an M dot J. All right. So this lemma is actually kind of well, it's not technical. I was expecting it to come up. I was expecting to use it like soon afterwards, and I don't see where I'm using it. So maybe it's not. Maybe I'll skip the proof. I don't know. So if I have a G module, I'm going to denote by M circ the same, as a Z module, it's going to be the same as M, but now I'm going to just redefine the G action to be the trivial action. Okay, so that's what it is. I've kind of stripped away the G action. I haven't taken the invariance. It's the same damn module, but the G action is redefined to be trivial. And then the lemma says that you could use that as well. So the induction into G of M0, right, is right. So here's what I'm saying. I'm saying maybe the right way to say it is like this. So I claim that these two G modules are isomorphic. Okay, so why do I write here when I write M0? I kind of didn't have to write M0 because in the expression for induction, I'm just supposed to be using a commutative group anyway, but it kind of is helpful to write M0. Why? What's really going on? Really what's going on is I'm comparing this is a tensor product of Z modules, so these things are definitely the same Z module. The only question is what's the G action, okay? Here, in general, right, remember I gave you a general recipe for the Z tensor product of G modules, and the tensor product should be the diagonal G action. So on the right-hand side, G acts on ZG, and it also acts on M. Okay, so like H, that's going to come up in the proof, I guess, but H acts on G tensor M by acting on both factors. Okay, so that's the G action over here. But over here, because I put the circ, then all of a sudden over here, I have a trivial G action. And so now the way that H acts on G tensor M is only through the first factor. Okay, but the lemma says, don't worry, actually those things are isomorphic as G modules. Okay, and then there's the similar claim for the co-induction. So the co-induction here is isomorphic to, so here this should be a Hom over Z from ZG into M with the trivial action. And here now I'm giving it the my usual recipe for the Hom. Yeah, maybe the second one is more interesting. So maybe I'll skip the proof of the, well, I'll just go through it very quickly. Why not? So I'm just going to define a map for you. So the map here is some weird G twisting. So it takes G tensor M, which again is, is like in general, it's defined by this, and a general element of this is a finite sum of guys that look like this. And so it defines it to, it takes it to G tensor G inverse of M. And so let's just check that this is a G equivariant map. So that should be easy. So H of this guy is H of that. Okay, and now let's see. So now I've applied the map already. So now I'm in the situation where the G action on M is trivial. So again, I let H act on the first factor, but I don't let it act on the second factor. Okay, and then that's the same as applying the map to HG tensor HM. Let's see. Is that, did I write what I wanted to write there? Let me see. HG tensor. Yeah, sorry, I'm kind of confused by that. Let's see. Shoot, is that what I don't think that's what I wanted. So V of HG tensor HM would be, no, it is, I'm sorry. V of HG tensor HM would be HG, and then I have a HG, the quantity inverse, which is G inverse H inverse applied to HM, and G inverse H inverse applied to HM is G inverse of M. Okay, sorry. So maybe I should have put in one more step or something, but yes, that's true. Yeah, this is just sort of simple and a little tedious. And anyway, and so then, now I'm on the left. I haven't applied V yet, and so the G action is diagonal. Okay, so just checking it. This map is a G equivariant map. That's great. And its inverse is this other map, which you can check as G invariant. So its inverse takes G tensor M to G tensor GM. Okay, so that's why the tensor is isomorphic to the tensor. What about the other one? So then I'm going to define a map here by, let's see, so if I have a map from ZG into M, which then I can think of this as being a map from G into M. And so I define it at G to be phi G of phi inverse. Just think about that for a second. Okay. Yeah, this is not a fun proof to go through. So maybe I'll stop. Maybe I'll stop going through it. But so you can check. What do? You check that again I've defined a G map, and okay, you check that I've defined a G map, and then what do I claim? I claim that again, the source and target are kind of the same Z module, and so they're both can be viewed as the collection of all maps from G to M. And then just at the level of G modules, you can immediately write down an inverse to this map. This map was sending phi to G of phi G inverse. So it's kind of plausible that its inverse should send phi to G inverse of phi of G. And so you check, again, just at the level of a billion groups. And then now, we do this uncategorical but correct thing. So I'm in the category of modules over a ring. And so yeah, an isomorphism is a morphism that is bijective in this category. So okay, yeah. So sorry, that wasn't super fun. And I guess I was sort of expecting a more immediate payoff, but this is kind of yeah. So this is kind of justifying the sort of strange action that we're doing here. So what am I saying? I'm saying that if you started with a G module anyway, then in the co-induction, you might as well have used the standard adjoint G action. That's the upshot of this proposition. Okay, so remember before I was saying, isn't it kind of weird that we're giving it this recipe for the G action, which is not the same as the recipe that we had before? Well, in general, we can't use the recipe that we had before, because for the recipe that we had before, both the source and the target should be G modules. Oh, there's something in the chat. Okay, bye. And so in this, but if both the source and the target are G modules, then we already had a G module structure, on this HOM. And then the question is, like, why weren't we using that? And that's what this lemma is saying. So this lemma is saying that in that case, it looked like we just kind of came out with a new G module structure out of nowhere, and in fact, it's isomorphic to the old G module structure. Okay, I really thought let me keep my eye on this. I'm pretty sure that Harari does make this remark as well, and so I think it might come up for something. So let me just go and just say I think we're almost done for today, but I just want to remind you. If anyone has anyone ever studied like the representation theory of finite groups? It'd be nice if you did. I guess, yeah, wasn't there a graduate course on representation theory of finite groups that was taught here like not that long ago? I think Lenny taught it. Anyway, so I've always found it really weird that in our department where representation theory is so popular, there's not like a standard second semester graduate course on representation theory of finite groups, because again, I took a representation theory of finite groups, like a half course on representation theory of finite groups back in the day. Anyway, so if you study, I mean, literally just, representations of finite groups on finite dimensional complex vector spaces, it's a classical but rich subject. If you've ever studied that, then not only does induction come up, it's not an exaggeration. It's like the most important thing in the entire subject. I recommend Sarah has a book, Linear Representations of Finite Groups. It's a beautiful book. And he's got kind of part 1, part 2, part 3 in different levels of difficulty. And the only interesting thing that he does in part 1 is introduce the induced representation. So it's really important. And so I think maybe I'll just end this lecture just by reminding you a little bit, or reminding you of things that you may not have seen, why the induction is important even in classical representation theory, in ways that actually are important to number theorists. Okay, so there's these theorems of Artin and Brouwer. So Artin's theorem is they each concern a finite dimensional complex representation of a finite group, so the most classical case of representation theory. So it turns out that this representation is a Q-linear combination, and I'm not going to stop and explain exactly what I mean by Q-linear combination. You kind of clear denominators and put things on the other side, and finally it makes sense, but I'll let you look this up if you want. So V is a Q-linear combination of induced representations, and then the question is, well, what kind of subgroups can you induce from? And so for here, in order to get a Q-linear combination, which is a, kind of allowing some stuff, then every Q-linear combination, every representation is a Q-linear combination of representations that are induced from one-dimensional representations of cyclic subgroups. Okay. So even if you've never studied representation theory, in like 10 minutes, you could master the theory of one-dimensional representations of cyclic groups. Okay, there's nothing going on. You're just studying a homomorphism from a finite cyclic group into the multiplicative group of the complex numbers. You write down the roots of unity. It's nothing, right? So that's up to this Q-linear combination, this is expressing every possible representation of our group as a certain type of combination of really, really simple representations. But again, I'm going over it quickly. The Q-linearity is not the greatest thing. It would be better to have, excuse me, it would be better to have a Z-linear combination of representations, okay? Okay. I mean, to make sense of this, you kind of have to take like the direct sums of a certain number of copies of this representation. So it's sort of like stabilizing something by taking a direct sum of copies of itself. It would be better not to do that. So Brouwer came along. These are right around the middle of the 20th century. One of his greatest theorems. So same setup, you have a finite group, you have a finite dimensional complex representation, then it's a Z-linear combination, so that's better, of induced representations. Now each W is a one-dimensional representation, so just kind of a character, like a true character, if you will, a homomorphism into C star. But the groups have to get a little bit more complicated. So the definition is what's called an elementary subgroup. Okay, what's that? It's the direct product of a cyclic group and a finite P group. Okay, but again, so both of these theorems are saying these are theorems that express an arbitrary representation of a finite dimensional complex representation of a finite group as a combination, in general, kind of, in this one, it's like a sum and difference, basically. So if you just put things on the other side, then you get, anyway, so you get like your representation, direct sum, a bunch of one-dimensional representations induced from subgroups is isomorphic to another direct sum of one-dimensional representations induced from subgroups. That's what this is saying. And so the groups are slightly complicated, but so what kind of information is that giving you? So I'll just say, this is the very result that Brouwer used in his study of Artin L functions. So if you have a finite dimensional representation over the complex numbers of a finite group, Artin attached an L function to this. If the representation itself is one-dimensional, then then it factors through the abelianization of the group, and then you essentially get a Dirichlet L function. So Artin L functions are non-commutative. The generalization to representations of finite non-commutative groups that Dirichlet L functions and I guess Hecke L functions are in classical number theory. So very, very, very important class of L functions. And so one of the most important conjectures in all of algebraic number theory is something called Artin's holomorphy conjecture. So you define these Artin L functions. Again, like the recipe for defining an Artin L function out of a representation of a finite group is no more complicated than the recipe of defining a Dirichlet L function off of a Dirichlet character. Okay, it's the same. It's basically the same thing. But of course, the functions are not as easy. And whereas people know that probably Dirichlet proved that every non-trivial Dirichlet L function has a analytic continuation to the entire complex plane, right? That's one of the main results of analytic number theory, right? If you take the trivial character, you get the Riemann zeta function, which has a simple pole at s equals 1. If you take any non-trivial Dirichlet L function, then it has a holomorphic continuation. So Artin's holomorphy conjecture is that the Artin L function attached to every non-trivial representation of a finite group has a holomorphic continuation to the entire complex plane. This is related to very, very deep algebraic number theory. And so this has been proved for like various particular results, like doing it for the icosahedral group A5 was like a big, fairly recent accomplishment, somewhat related to Langland stuff. The best general result is due to Brouwer, who showed that, okay, you want a holomorphic continuation, but he showed that every single Artin L function at least has a meromorphic continuation, okay? So, possibly with poles to the entire complex plane, and he deduced that as a fairly easy corollary of his induction theorem. Okay, so what I'm trying to say is that inducing representations is like the most important thing that you could possibly do in representation theory. And I guess I scratched out this thing because I didn't want to talk about it next. But there's sort of a question here. So I defined induction and I defined co-induction. I haven't really done anything super great with either one of them yet, but I've indicated that even in the setting of classical representation theory, induction is incredibly important. Where's the co-induction? Why does classical representation theory speak of induced representations, but not of co-induced representations? Well, there's a good answer to that, and that will come up in the next lecture. And then also in the next lecture, we'll prove Shapiro's lemma, which explains the importance of induced and co-induced representations in group homology and group cohomology. Okay, well, that was a long lecture, but we're on our way. See you next time.